That doesn't sound good at
That
all.
does not sound good.
That sounds like
Contact tracing. And so I didn't get to record, so that's why I'm recording now.
Someone did make us
connected her computer.
Yeah, some little person in her second period.
Okay.
They just, I wrote my thank you letter to her.
Aw.
Yeah, I see.
Oh, she'll like that. All right, so let's look at these real quick. So,
Send it back with a grade on it.
was everything spelled right?
Oh my god.
I was so scared when I was writing it. I was like, oh my god, that doesn't look right.
Yeah,
Let me just rewrite
She's
it.
she's circling red pen.
I was gonna say,
Minus one.
make sure that it's spelled right and correct.
That's
Too late.
All right, so what do we put in the middle? P. F. And like I said, your F could have gone on the bottom. I mean, the top, that's fine. So once we've done that, count it, put our central atom, attach everything. Now I'm going to start filling up the octets for my terminal atoms, which means my ones that are not in the middle. So I've done that. So each fluorine has 8 around it. So 8 times 3 is 24. So that means I have 2 more left, which would I put right there on my phosphorus, which is what it needed, right? Now this one, boron, this is one I've been trying to do all day. 24. So same thing. What am I going to put in the middle?
B.
B. And then I'm going to attach my 3 chlorine with single bonds.
Oh, wait, boron can have 6.
Boron, I'm giving you a Lowry loop for that. You're the first person that's remembered that or said it out loud. So now here, same thing. I gave all of my terminals. So every one of my terminals, my chlorine have 8, but my boron only has 6. And that is okay because it's an exception. So this is a good structure right there. It doesn't have to have those 2. It can just have 6. So, and remember when I draw a circle around it, that's not part of the structure. I'm just showing you valence electrons. All right, so today we're going to take it one step further. Welcome. So if you get your notes out, we're going to skip. Oh, wait, one thing before I forget. A quiz on Thursday is not over what we're covering tomorrow. It stops today. So just what we covered yesterday and what we covered today. And it is open notes. So there will not be a re-quiz. It's 20 multiple choice questions, but you know, they're going to take a little longer because you're going to probably have to have scratch paper to draw out some structure. So you have 15 minutes on that. I think, yes. If you haven't done your practice, it's going to be kind of hard to get through that. Okay. But we're not doing re-quizzes whenever we do an open notes quiz. Now let's get to our notes.
Did you do that just so we would have to re-quiz after the break?
Did I do that just so you wouldn't have to? No, I did it because I decided it could be open notes.
Yeah, it is.
I mean, anyway, okay, so we're skipping. If you look where we stopped in our notes, I know these notes are a little bit out of order, but my friend types them all up, and then she gives them to me, so I do not fuss because I'm not retyping all that. So we're skipping on the back page, Roman numeral 5. It says molecular geometry. We will do ionic tomorrow. And people usually think ionic is easier than covalent. Hopefully you'll feel that way. I do feel that way. So we're going to be talking about molecular geometry or the shape. And this applies only to covalent compounds. So whenever we do our ions, our ionic compounds together, we won't talk about what their geometry is because they just form ions. It's on the back of the second page, I think. Did you find it? Roman numeral 5? Okay. So Lewis structures, we talked about that's what we did already. Or electron dots are used to represent the molecules. And we know the dashes or dots can be used to show the bonds, and then we can have our lone pairs of electrons. So molecular geometry is the 3D arrangement of the molecule's atoms. So how those atoms actually are arranged around the central atom. And then after we get back from Thanksgiving, we'll spend a little bit of time on molecular polarity which is the uneven distribution of the molecular charge. Today we're looking at the shape or the geometry of those molecules. So we use this using the VSEPR theory, which stands for valence shell electron pair repulsion. Much easier just to call it the VSEPR theory. And this states that the repulsion between sets of valence level electrons in surrounding areas causes them to be oriented as far apart as possible. You have to think you have electrons that are in the bonds and then lone pairs of electrons. So a bunch of negative things together are going to repel each other, and they're going to be oriented as far apart as possible. And that's going to determine the shape or the geometry of the compounds. The lone pair of electrons occupy space around the atom just as the bonding pair do, and both of them are going to determine the actual shape. But lone pairs have more, or they have more repulsion, or they repel stronger than the actual ones that are in the bonding. And a good example of this is if we look at water, which is an oxygen with 2 hydrogen, and then it has a couple of lone pairs still around it. So this would be linear, just straight across. But yet we all know that really the shape of a water molecule is like this. We call it bent. You might want to. And the reason it is like this is because these lone pairs of electrons are repelling those electrons that are in the bonds, and it's causing them, instead of allowing them to just be straight across, it's causing them to bend. So those lone pairs of electrons have an effect on the shape, and that's kind of what we're looking at today to determine those different shapes. Are we good? All right. So we're going to switch off over to our little sheet. So this will become part of your notes. All right. So if you notice here, we would use VSEPR only for molecular shape. So that's if they have covalent bonds. And we're always looking at what happens around the central atom, not one of the terminal atoms. We're interested in the central because that's where everything adjusts itself, and that determines the shape. We're going to be looking at the molecular shape. So we are not interested in electron geometry. So if you want to mark that out, you can. So the first thing that we always do is we determine how many domains a central atom has. And a domain is equal to a bond, any kind of bond, or an electron pair. So for instance, if I just look at this one that they have drawn here, in the center where your A is, if you notice A is the central, and then everything else is X is what's attached. Here I have A in the center, and it has 1, 2, 3 things attached to it. It has 3 bonds, so that means it has 3 areas of electron domain. Same thing here. Here I have my center one. It has 1, 2 bonds, and it has 1 lone pair. That is still considered a domain. So that is still 3 areas of domain. And that bond can be a single bond, a double bond, or a triple bond. It doesn't matter. They're all just considered one domain. Okay? Once you determine that, then you're going to have to take a step back and you're going to see what kind of, whether it was bonds that made up one of those domains or lone pairs that made up one of those domains. So in other words, we said this had 3 areas of domains because it had 3 bonds. So once I determine it had 3 domains, then I'm going to come over here and say, okay, all 3 of those were bonds. none of them were lone pair, so that means it's going to be triagonal planar. As compared to this one still had 3 areas of domain because it had 2 bonds and electron pairs. But now I need to come and say, okay, it only had 2 bonds and it had 1 electron pair. So instead of triagonal planar, this one would be bent. That lone electron pair has made it change from what it would be without that lone electron pair. So we're going to be using this area. We're going to be using this column. And then you'll want to look at your bonded atoms, your lone pairs, and then your molecular shape. Okay, so let's look at some examples of those. It's not so bad once you get started. Let me find y'all. Oh, let me get out of here. Is that chunky? All right, so we'll start here, and this is on your practice from today. So obviously the first thing you got to do is you got to draw your Lewis dot structure. If you don't do that, you can't look at the rest of it. So carbon tetrachloride, carbon in the middle, 4 chlorines. Just giving them their octets. All right, so that would be how you would draw your structure. Now, whenever you start determining your molecular geometry, you're only interested in the central atom. I'm not interested in any of those terminals. So on this central atom, I have 1, 2, 3, 4 things attached to it. So that means I have 4 domains. And domains is just short for electron domains. Of those domains, they're all bonds. So I have 4 bonds, 0 lone pairs. On this particular one, on the central atom, there's no lone pairs. I'm just writing this to teach. You don't have to write that because at the very end of it, you want to say what its molecular geometry is. So now once we've determined all that, we would go to my little cheat sheet, if I can find it. And I would say, okay, where am I at? Okay. I said I had 4 areas of domain. So that puts me in there. There's a lot of different ways they could be. But on that particular one, they were all bonds. So that would make it tetrahedral. So you want to find out how many things are attached to it. And once you've done that, then you need to determine how many of those are bonds and how many of those are the electron dot. Or the lone pairs, I'm sure I should say. All right, we'll look at another one. We'll go down to NH3. NH3, that was on your practice yesterday. All right, if I look at it, it has 1, 2, 3 bonds, so that's 3 areas, and it has a lone pair. A lone pair counts as an area also, or domain. So it has 4 domains. 1, 2, 3, and then this bond is a domain. So it has 4 domains. Of those, 3 are bonds, and 1 is a lone pair. So now once I've kind of determined all of that, then I can go back and I can look at my sheet. And so now I say, okay, well, I'm still here in my 4, but it's not going to be tetrahedral because I don't have all 4 of them are bonds. Now I had 3 that were bonds and 1 that was a lone pair. So now that one is going to be Trigonal, pyramidal. I don't think any of these get up that much. You want to do one more? Huh?
Please.
It's really easy, but
Yeah.
I don't wanna chance it.
Someone get home and I'm good with it.
All right, let's do water.
Do 11.
Do, yeah, no, do 9. Do this 3 of them.
I thought I just did 9 or one like 9. Really, I promise you, water's a good example. We haven't talked about its shape. Well, we did mention its shape. But so how many domains does it have? 4. It still has 4, even though all of these that we've looked at, they all have 4. They all look very different, right? So this one still has 4, a bond, a lone pair, and a lone pair. So this still has 4 domains. And this is split. 2 bonds, 2 very messy lone pairs. I'll put LP for lone pairs. So I'm still in that 4. I'm still here with my 4 because that's pretty common. But now which one's it going to be? Bent. Because we said we had 2 bonds and 2 lone pairs, so it would be bent. All right. So you got a little bit of time to do some practice on that. And then you do have a lesson check that you will do, and it is for a grade. So I'll be watching the clock. If you would like for me to personally work one with you, I will be more than happy to do that. If you want to bring it up here, we can work through one. It's one of those things, unless you jump in there and start giving them a try, it's kind of hard to get it. So if this is my 6th period watching, don't forget to go and do your lesson check.